Hello all, I'm Yogesh Singh. Welcome to my YouTube channel, Yogi's Data Lab. So today we are going to talk about the partial derivative method to minimize the squared sum of errors. Now what happens is we are going to take only a simple linear regression where we'll have beta 0 and beta 1. We'll use partial derivative to calculate the formula for beta 0 and for beta 1. We can increase this to all the variables or multivariate analysis or the multivariate linear regression also. But the problem is you'll get n number of equations where n is the number of variables that you have. And eventually you'll have to solve all those set of n equations to get n plus 1 values where the n plus 1 comes with the beta coefficient or the intercept along with the beta coefficients that you're getting. So here we are going to look only into a simple method where we are looking at beta 0 and beta 1 for the calculation. For an entire multiple variable linear regression analysis, it is better to use the matrix method, for which I have already shared the video. I'll put that link in the description. You can use that to understand how your multiple variable linear regression runs. For a simple one, we'll prefer to go with this method, though you can even do that using your matrix method. But this is one more method which you should know as to how we are solving this. So let us begin. Okay, so let us start with the basic linear regression line where I say yi is equal to beta 0 plus beta 1 x1 or beta 1 xi plus epsilon. Epsilon is your errors, beta 0 is your intercept, beta 1 is the coefficient for x1 and or xi, and xi is your variable, independent variable, which is contributing towards your dependent variable. Now, when I talk about the squared sum of errors, what is it? It is actual minus the predicted. And I am summing up the squares. So if you look at this, this is my actual. And this value, whatever is the equation that I get, I can use that for predicting my value. So I can say this is my predicted value, beta 0 plus beta 1 xi. And I am doing a square. So yi minus y cap whole square. And I am summing up the values. Now, what will you want? You want that the error should be minimum, right? I want to bring the errors to the minimum value, which could be 0. To bring this to a minimum value, let us say you have been given the data set. You have your entire data. You have your x's, which are your independent variable. You have y, which is a dependent variable. So what you are going to look into this situation with your x's and your y is that the x's and the y will be constant. They're not going to change, right? Because that is the data that you have received. That doesn't change. The only thing that I can play around with is the beta coefficients, which I can minimize or maximize. So I want to minimize my values over here, this difference, so that the errors are minimum between the actual and the predicted. It has to minimize in a way that the errors can be as close as 0. So to do that, what we are going to do is we are going to do a differentiation. Now here, if you see, I'm doing a partial derivative. I'm not doing a complete d by dx or a differentiation, but I'm using del by del beta 0. Now, why am I doing this? Because if you look at this equation, which is your loss function in a way, or your errors in a way, what we are doing is we have this equation as dependent on two parameters, beta 0 and beta 1. It is not only dependent on a single value. If it is dependent on a single variable, I can go ahead and do d by dx or d by dy. But here I am depending on two parameters, and since it is dependent on multiple parameters, I will go ahead and use a partial derivative, not the complete derivative. So I'm doing del by del beta 0 and I'm putting my equation over here. When you differentiate this, you will get this value, which is minus 2 summation I to 1 yi minus your beta 0 plus beta 1 xi. Now this value, the minimum value that I can achieve is 0. So I'll set this value to 0. So what will you get? You'll get this equation equated to 0. When you solve this further, I have moved minus 2 to the denominator. So this is left with only this equation. So you see, you have summation I equal to 1 to n yi minus beta 0 plus beta 1 xi equal to 0. Now let us expand this equation. So when I'm expanding this, what I see is summation I equal to 1 to n yi minus I equal to 1 to n beta 0 minus I over 1 to n beta 1 xi equal to 0. So this remains as it is. Let us leave it as it is. This part remains as it is. Now this thing, this term becomes n beta 0. Why n beta 0? Beta 0 is a constant value and I am summing it n times. So if you're summing 1 n times, what will you get? You'll get n. Similarly, if I am summing n times beta 0, what will I get? N beta 0. So this term becomes n beta 0. Now what I'm doing is I am just moving this n beta 0 at this part. So you get n beta 0 is equal to summation of yi minus summation over beta 1 xi. Now we have n beta 0. Let's expand this. So we got this equation. So what I'm going to do is I'm just going to bring beta 1 outside over here. So it becomes n beta 0 is equal to summation I equal to 1 to n yi minus beta 1. So beta 1 is a constant. We brought it outside. Summation I equal to 1 to n xi. Further, move this n to the denominator. So you get summation I equal to 1 to n yi by n minus beta 1 summation I equal to 1 to n xi by n. So if you look at this part is nothing but the average of y or the mean of y. And this is the mean of x. So I can say that beta 0 is the average of y minus beta 1 average of x. So this is one equation that we got which tells me what is the formula for beta 0. So this is the result when I differentiate my loss function with respect to beta 0. Now let us try to differentiate the loss function with respect to beta 1. So let us see. So this time it is del by del beta 1. And again, the same loss function has been put here. So what are we getting? We are getting this value minus 2. Again, the same equation, nothing extra, but you will get one xi over here because we had beta 1 xi, right? So when I'm differentiating this, you'll get an additional term xi this time. So I'm setting this again to 0 because that is the minimum value that I can get. So this equation that we just differentiated, this part, which is over here, is equal to 0. So when you expand this, you get summation yi minus beta 0 minus beta 1 xi multiplied by xi equal to 0. Let's multiply xi over all the terms inside. So you see summation yi xi minus beta 0 summation I equal to 1 to n xi minus beta 1 summation I equal to 1 to n xi multiplied by xi will become xi square is equal to 0. Now beta 0 we already know is nothing but y bar minus beta 1 x bar. So let us go ahead and put the value of beta 0 over here. So remaining all the equation remains same. I have just put the value of beta 0 over here, which is y bar minus beta 1 x bar. Let's open up this equation. So what do you see? It is summation I over 1 to n yi xi, which is the first term. Then minus y bar multiplied by this term. So minus y bar summation I equal to 1 to n xi. Then minus and minus becomes a plus. You get a plus over here. And beta 1 x bar multiplied by summation I equal to 1 to n xi minus beta 1 summation I equal to 1 xi square over here. And this equation is equal to 0. Now we are going to try to simplify this equation further. So what I have done here is I have expanded this part. This is over here. You see yi xi minus y bar xi. You have this here. And I have taken out beta 1 minus beta 1 common from these two terms. So when you pull this out minus beta 1, it becomes summation xi square minus x bar summation over xi equal to 0. So you can write it this way that beta 1 summation I equal to 1 to n xi square means this term, you will move it to the right, will be equal to this remaining part which is here, which is summation I equal to 1 to n yi xi minus y bar multiplied by summation I equal to 1 to n xi. Now this is looking a bit complex, so we'll break it down. Let us solve the left side of this equation. So I'll try to solve this part, beta 1 and this part. We'll solve this equation. So I'm picking up this part, summation I equal to 1 to n xi square minus x bar summation I equal to 1 to n xi. Now what is x bar? X bar is nothing but summation I equal to 1 to n xi by n. So we'll put that value over here. This gives you summation I equal to 1 to n xi square, which is the same term. You see here, this is what you have, minus 1 by n, and summation I equal to 1 to n xi, the whole square, because this entire term is twice, so it will become a square, and 1 by n is the denominator. So this is one part of the equation which we have solved. Now, there's a slight trick here. Let's try to understand this. If I consider sum of squared deviation, deviation means I'm moving away from the mean, right? And xi minus x bar, that is the movement from the mean. I'm doing a square and I'm summing it up. So this is that equation, sum of squared deviation. When you expand this, since it is a square, using a minus b whole square, which is a square minus 2ab plus b square, you will get xi square minus 2xi multiplied by x bar plus x bar square. So I wrote it x bar multiplied by x bar. Somehow I was not able to write x bar square using the mathematical formula. So I wrote x bar multiplied by x bar. So now this summation will apply everywhere. So you have summation xi square, which is the first term, minus 2x bar. So x bar is constant, it has come out, and I have summed it over xi multiplied by summation I equal to n x bar multiplied by x bar. And let's try to simplify this. So this is the same term, nothing changes. X bar is what? Summation I equal to 1 to n xi by n. So I've just put the formula over here. And x bar is an average. Average of any series is always going to be constant. It is going to be a number. So I'm summing it n times, so it becomes n x bar multiplied by x bar, means n x bar square. Now, when I further simplify this, what you see, the first term is as it is, nothing changes, minus 2 by n, and this will get multiplied with this, so it becomes summation I equal to 1. So this is going to be 1, I equal to 1 to n xi square plus n by, now I have opened the formula of x bar. If you open x bar, it is summation I equal to 1 to n xi by n. So this whole term will be squared. So what you see, this square, when it opens up, it will become summation I equal to 1 to n xi square. The denominator will be n square and the numerator will be n. So this will cancel out and it becomes 1 by n summation I equal to 1 to n xi whole square. Now this is plus 1 by n, this is minus 2 by n. So it will solve and it will give you this equation, summation I equal to 1 to n xi square minus 1 by n summation I equal to 1 to n xi the whole square. When you look at this, this is the same term that you saw here. Okay, so in a way, I can say that summation xi minus x bar whole square means this term over here, squared sum of deviation, this is equal to this term, right? So the left side, I can write it in a simple term, which says that it is this. If I divide both sides by n, I'm dividing this side, the left hand side and the right hand side by n, what will I get? This part becomes variance. This is the formula of variance of x. So variance of x is equal to 1 by n of the right side equation. So if I want this value, which was there in equation 5, it means it is n times the variance of x. So if you look at this equation 5, this one, you can write that it is n times the variance of x. So that is what we just proved. Now, this part has been proved that the left side I can write as n times variance of x. Now, what was the actual equation? Let's go to equation number 4. So I can write beta 1 into n times variance of x, because this I know is n times variance of x, is equal to this part. So let us go ahead and write this. So beta 1 n times variance of x is equal to this part, which was the right part. Now let us solve the right part of the equation. So the right part of the equation is this. I've just written it here. Now when you open up y bar, what will it become? It will become minus 1 by n summation I equal to 1 to n yi, again a summation I equal to 1 to n xi. Now covariance of x and y, how is it given? It is given by 1 upon n summation I equal to 1 to n xi minus x bar multiplied by yi minus y bar. So let us expand this again. So you'll see 1 upon n xi multiplied by yi. So summation I equal to 1 to n xi yi minus x bar summation I equal to 1 to n yi minus y bar. This term will get multiplied with this. So minus y bar summation I equal to 1 to n xi plus n x bar y bar. So y n x bar y bar is negative, so it becomes a plus, and it is a summation of 1 to n. So it is a constant because both of them are means, so it becomes n x bar y bar. Now let's expand this further. So I'll open up what is x bar, I'll open up what is y bar. So this is what I have written here. I have opened up x bar minus 1 by n summation I equal to 1 to n xi. Y bar when opens up, it is here 1 by n summation I equal to 1 to n yi. And this we already have opened up, which is n x bar y bar. So summation I equal to 1 to n xi by n and summation I equal to yi divided by n. Now let's solve this. So when you solve this, what will you get? This term, since the denominator is a n square and the numerator is n, it will become 1 upon n summation I equal to 1 to n xi and summation I equal to 1 to n yi. This part, this is that part. This thing is solved here, this thing. Now let's solve the other one. So this term is common. So these two will sum up. So it becomes minus 2 by n summation xi yi. Now since this is minus 2 by n and this is plus 1 by n and the terms are common, this will become minus 1 by n summation xi yi. Now what is this that we are solving? This is nothing but covariance of x and y. So I can say that n times, if I move this n to the left side, n times covariance of x and y is equal to this part of the equation. Now what is this? This is nothing but, if you look at this one on the right side that we were solving, summation I equal to 1 to n yi xi minus y bar summation I equal to 1 to n xi. So this is the same equation that you are getting here. So I can say that the left hand side, which was beta 1 n times variance of x, is equal to n times covariance of x and y. So n gets cancelled out and beta 1 becomes covariance of x comma y divided by variance of x. So we saw that beta 0, which we calculated here in the very beginning, was y bar minus beta 1 x bar. And using this, we solved further what is beta 1. Beta 1 is covariance of x comma y divided by variance of x. Now if I go ahead and open up this formula, I'll see that the n cancels out. Obviously, it is by n in both the sides, so it is getting cancelled out. And you will be left with only this term. So I can further write that since R, which is my covariance of x and y, divided by the standard deviation of x and standard deviation of y, and beta 1 is covariance of x comma y divided by variance of x. So I can say this can be written as R multiplied by standard deviation of x and a standard deviation of y, because when you move this up, it will become covariance of xy. And the denominator, which you are looking at, is nothing but standard deviation of x whole square. So beta 1 is your correlation coefficient multiplied by the standard deviation of y divided by the standard deviation of x. So this is the derivation which you can do using partial derivatives. Now what we are going to do is we are going to look at when we solve using this method of covariance divided by variance and try to calculate the beta 0 and beta 1, and we try solving it using Sklearn, what is the difference that we get? So let us look at that. Okay, so here when you look at this, what we are doing is I have generated some numbers. So you see I have generated some numbers with a seed, and I am creating some random numbers with some noise. I'm adding a noise to it, and I'm generating some numbers. And now what I'm doing is for x, this is my x's and this is my y. So what I'm doing is I'm calculating the mean of x and I'm calculating the mean of y. Further, I'm calculating the covariance of x and y, and I'm calculating the variance of x using the formula that we know. Then beta 1 should be covariance of x and y divided by variance of x, and beta 0 is y mean minus beta 1 multiplied by the mean of x. So I get my values over here. So beta 0, which is my intercept, is minus 5.99, and beta 1, which is the coefficient, it is 3.018. Now this was the manual method, all that mathematics that we did and tried to understand how beta 0 and beta 1 is calculated. Now let us try this solving Sklearn. So I am reshaping the data over here. I'm reshaping it for the purpose of Sklearn. And now I am running linear regression and I'm fitting the intercept. So I am fitting the model over here. And if you look at the intercept at this point, I have printed the intercept and the coefficient for the model which I have fit. The intercept is minus 5.99 and the coefficient is again 3.018. So if you compare the results for your x and y, whether you do a manual calculation using the covariance and the variance method, or you use Sklearn, you see that the results that you are getting both are same. So this is one way of what I wanted you to see exactly how this is solved using the mathematical part. And when you're solving it in Python, you can still do it using Sklearn, which is much simpler, you see, not much of an effort to be done. But it is good to understand how these things work behind the scene. So I hope you enjoyed this video. You were able to understand how to use partial derivatives to calculate your beta 0 and beta 1. So if you did like this video, please do like, share, and subscribe, and see you in the next video. Thank you.